Today we're going to look at section 9.7, which is solving systems of equations with inverses. So to start, we need to identify something important called the identity matrix. And this is kind of a weird thing because it has a singular name, the identity matrix, but it's actually many different matrices that all have the same form. Your book differentiates between different size identity matrices with a little subscript. So this first one on the left, the book refers to that as I sub 2 because it's a 2 by 2 matrix. And then the one on the right would be I sub 3 because it's a 3 by 3 matrix. And you could keep going with larger and larger matrices. The important thing about the identity matrix is that it is the multiplicative identity, meaning if you multiply any matrix by the identity matrix, the result is the same as the original matrix. Okay, so it's like thinking outside of matrices for a second. If it's just regular arithmetic, it's like multiplying by 1. Okay, so multiplying by the identity matrix always gives you the original. And that's true whether you're multiplying, like say you have matrix A. All right, so if matrix A, let's just say it's a 2 by 2 matrix, A times I will give you A, and I times A will give you A. Usually, matrix multiplication is not commutative, but when we're talking about multiplying by the identity matrix, it is. So the identity matrix is an important matrix. It's good to know. Got to be familiar with the identity matrix. All right, so part of the reason we have to talk about the identity matrix is because in this section we want to talk about inverses, and the inverse matrix definition uses the identity. Okay, and in a nutshell, basically what we've got is that a matrix is matrix A inverse. Okay, A to the negative 1 is A inverse. Is the inverse of matrix A if A times A inverse equals the identity matrix. Or let's say you had matrices A and B. Okay, A and B are inverses of each other if, when you multiply them together, you get the identity matrix. Okay, so only square matrices will have an inverse. So a 2 by 2, a 3 by 3, a 4 by 4. You cannot have an inverse that is a 2 by 3 or a 4 by 5 or anything like that. Okay, it always has to be square. But not all square matrices have an inverse. All right, and in fact, we have a special name for matrices that do not have an inverse. We call them singular. All right, so inverses are a pretty important concept here for matrices. So we need to talk about how you go about finding a matrix, the inverse of a matrix. So in this example, I'm actually going to show you 4 different ways that you can find an inverse. I really only expect you to use one of those ways, though. And once you see the example here on the document camera, you'll understand what I mean. Okay, here in example number 1, we have a matrix A, and we want to find the inverse of this matrix if it exists. Okay, it's not guaranteed that a matrix will always have an inverse. So just be aware of that. So to begin this example, what we want to do is, I actually want to show you a couple different ways that we can go about finding this inverse. The textbook shows you 3 different ways if you take a look. The first way is by matrix multiplication. All right, based on the definition of an inverse, what I should be able to I'm going to say this is like case 1. All right, so this is the first method that we'll use. What we should be able to find is a matrix such that when we multiply these things together, we get 1, 0, 0, 1. Right, that's the identity matrix. So using the definition of matrix multiplication, we would multiply 2, or let's say the first row times the first column. So 2a plus 7c. And then the first row in the second column, so that would be 2b plus 7d. and then bottom row 1, 4 times AC here, so it would be A plus 4C, and then B plus 4D. Okay, and that should equal 1, 0, 0, 1. So what that means is we now have a couple of systems of equations. We have 2A plus 7C equals 1, and A plus 4C equals 0. And then we have 2B plus 7D equals 0, and B plus 4D equals 1. So I'm just pulling this from this entry is supposed to equal 1, this entry is supposed to equal 0, so that's where the top two come from. This entry is supposed to equal 0, so that's there. This entry is supposed to equal 1, so that's there. So now we have a couple of systems of equations that we can solve. All right, so that's case 1. I'm going to stop there because you guys know how to solve two variable systems, and you don't need me to necessarily show you how to do that. So I'll let you finish that from there if you so choose. For case 2, the second way that we can find an inverse, we are going to use an augmented matrix. Okay, so we're going to turn 2, 7, 1, 4 into 2, 7, 1, 0, 1, 4, 0, 1. Okay, if we just kind of dotted line that, we see that to the right of that dotted line, we have the identity matrix. So what we want to do now is we want to use row operations to turn this into 1, 0, 0, 1, and then let's just call it A, B, C, D, and A inverse will be A, B, C, D. All right, so we did our row operations in the calculator using row echelon form, and so you could do that with this as well, although there is a second feature in there called reduced row echelon form that would actually be better than the REF, reduced echelon, that we used, because row echelon form would get you the 1 here, but not necessarily a 0 there. You would have a 0 here, so the bottom row would be correct. The top row, you might have to do a little more work to. Okay, so that would be case 2, and if you want to use the reduced row echelon form to get that, that's fine. However, there's a third case that works specifically for 2 by 2 matrices when you're trying to find an inverse for a 2 by 2. So case 3, we actually have a formula that we can use. All right, and the formula is based on something that we're actually going to talk about in section 8, which is the determinant. Okay, so given, I'm just going to say, given matrix A is A, B, C, D, the inverse of A is 1 over AD minus BC times DA negative B negative C. So this this AD minus BC that you see here, that is the determinant. Okay, we're not technically calling it that yet. We're not really talking about the determinant until next section, but just as a just sort of as an advance warning, that AD minus BC, that's the determinant. And it kind of brings to light why some matrices don't have an inverse. Because if AD minus BC equals 0, then we're dividing by 0 right here, and there must not be an inverse because we can't divide by 0. So that's the third case. The fourth case is using the calculator, and that's honestly, that's the case that I would expect you to use. Especially considering that there is a button on the calculator specifically for finding inverses. So what we're going to do is, we're going to, let me clear that out. That's something I was working on earlier. What we're going to do is we're going to go to the matrix menu. We're going to put in a 2 by 2 matrix in the edit window, And this needs to be our example, which was 2714. Okay. And before we do anything else, it's always a good idea to check and make sure that we have typed our matrix in correctly. So not incorrectly, but we have typed it correctly. So 2714 is our matrix. And then to find the inverse, it's as easy as this. You go matrix A, and then this little x to the negative 1 button is the inverse button. So if you hit that, you get A inverse, hit enter, and there we have it. The inverse is 4, -7, -1, 2. So all three of these previous methods that I showed you would get you to this solution. And I wanted you to kind of see that they're there, that they exist. There are ways to do these by hand. However, when you get into bigger and bigger matrices, when you get to 3x3 matrices or 4x4 matrices, doing these by hand becomes really, really tedious. So I expect that you guys will favor the inverses, the inverse button rather, in the calculator. So that's the method that I expect that you'll use most of the time. If if you want to try to do a couple of these by hand just for quarantine kicks, go for it. All right, so now we want to solve a system of equations using an inverse matrix. We're going to switch back to the document camera here in just a second. But the idea is we can solve a matrix equation just like we solve regular equations now that we have this multiplicative inverse. Okay, this idea of, and I see that typo here now, unverses. Whoops, it's supposed to say inverse. The inverses. The multiplicative inverse is something that would allow us to take an equation like ax equals b in this case and get rid of the a. Okay, turn it into just x equals some other matrix. So again, we're going to switch to the document camera to solve this equation and figure out what the solutions are to this system. For example number 2, we want to set up a matrix equation from our system of equations that we have here, and we want to do that by creating 3 different matrices from this system. Okay, the first matrix, which we're calling A, is the coefficients from the x's and the y's. The second matrix is the variable matrix, which I've named it X. Doesn't have to be X. You can name it some other thing if you want, but since we usually start with X for our variables, I'm using X. And then the third matrix is the constants on the other side of the equal sign. So in this case, 5 and 12. So if we use matrix multiplication, we would see that this equation is true. Okay, if we multiply a times x, we get 2 times x and 1 times y, which would be the first part here. And if we set that equal to b, that would be equal to 5. So 2x plus y equals 5. For the second one, -4 times x, 6 times y would give us -4x plus 6y. And setting that equal to b would say that it's equal to 12. So hopefully we see that this matrix equation is true. And now what we want to do to solve this matrix equation is we want to multiply both sides of this equation by A inverse. Okay, now we have to be careful with the way we do this because matrix multiplication in general is not commutative, right? So if I multiply by A inverse on the left-hand side, then I have to multiply by A inverse on the right-hand side of the equation as well. So now, we know that A inverse times A is going to be the identity matrix. Okay, and we also know from our discussion earlier that anything times the identity matrix is just going to be itself. So this equals x equals A inverse B. So to solve this system of equations using an inverse, what we need to do is put A and B in the calculator. So 2 by 2 for A would be 2, 1, -4, and 6. And then for matrix B, that is a 2 by 1 matrix with 5 and 12. Okay, so then we're going to check and make sure that our matrices are typed correctly. So 2, 1, negative 4, 6, that looks right. And then matrix B is 5, 12, that looks right. So to find x, I just need to do this. I need to do A inverse times B. So matrix A inverse times matrix B. And that gives me 1.125, which I don't really like, so let's make it a fraction. Gives me x equals 9/8 and 11/4. Okay, that's the variable matrix. Okay, so what that tells me is, since the variable matrix is x and y, then x equals 9/8 and y equals 11/4. So my solution would be 9/8, 11/4. For a third example, we're going to solve a 3-variable system, and you're going to see on this example that these things scale up really nicely. Okay, they don't get terribly more complicated just because we have more variables. So it's one of the nice things about solving with inverses is that the procedure doesn't get any more difficult when you get larger systems. So let's switch back to the document camera and see how this one goes. For example number 3, we're scaling things up a little bit. We're solving a 3-variable system of equations. So I've already gotten started here by writing out the 3 matrices, A, X, and B, that we would create from this system. And again, the matrix equation doesn't really change from problem to problem. This is still AX equals B, and multiplying both sides by the inverse and simplifying, we're again going to get x equals A inverse B. So that's pretty universal, and so you do not need to write out the matrix equation every time and solve for x, because it's pretty consistent. So I've gone ahead and gotten a head start here and typed these matrices in, but we can verify real quick that they're correct. There's matrix A. There's matrix B, 35, negative 26, negative 7. So matrix A inverse matrix B gives me 1, 2, 0. So x is 1, 2, 0. So that means our solution is the ordered triple 1, 2, 0. All right, so there's only a few things in this section. There's finding inverses, there's solving systems using inverses, and there's one additional thing in the homework section that I didn't cover, and that's just verifying. All right, I said I covered it, I guess, but I didn't give you an example of verifying that 2 matrices are in fact inverses of each other. And the way you do that is just by multiplying them. So there's a section at the very beginning that says verify that the 2 matrices are inverses, and honestly I don't even remember if I assigned you any, but if you see that, just notice that all you have to do is multiply the matrices together and show that you get the identity. All right, and then after that you're finding inverses, you're using inverses to solve, and then the very last one, 55, is a word problem where you're solving a system related to a application problem, and you're supposed to use inverses to solve that. Okay, so hopefully this will go well for you. I think this section's pretty straightforward, and talk to you guys soon, and we'll wrap up chapter 9 here shortly.